over IPSec tunnel steps.
We are
The things that can hopefully come away from you can actually go to the team, so you can focus on bigger stuff.
Hi.
I was just thinking as we were going and setting up the 58, 56, 54, 50-some tunnels between New Jersey and the new AWS system, and I'm going through copying and pasting, find and replace. But like, you know, it'd be a good idea if everybody just kind of at least understood how IPSec tunneling works, since it's a big part of, you know, IT nowadays.
Yeah.
And it's,
and it's recording.
Okay, I got it.
cool.
You look like an artist.
That one day. My picture.
Look at the guy.
Please.
Don't worry, you're getting the Zoom account, brother. You're going to be putting the picture up too.
Oh, no. There's no state picture of me. There will be no Zoom.
No Zoom picture. She want people to see the real Wes. Wow, you got Mike here too. Mike who? Sunita, I'm assuming. You can hear it.
So I don't know, how many people do we have?
I'm looking at
Looks
9.
like 7. Is that what that little 7 means down there?
Yes. Here's my participants list.
All right, cool. All right, what's enough to get started? All right, so the idea, what I want to talk about today is how IPSec tunnels work. It's a way that we take private traffic, encrypt it for live, transmission over the internet or any other medium that we might consider to be insecure. It starts basically 3 basic steps. First, you have to authenticate the peer on the other side. Make sure I'm talking to who I say I'm going to talk to. Make sure I'm going to build my tunnel to the person that I actually want to build my tunnel to. And so there's 2 main methods for doing that. Then we talked about key exchange, which is, okay, now that we've talked to each other over the internet, we know that we're going to talk to the person we want to talk to. How do we build an encryption key? Sensitive. If I don't have a secure method of sending a transmission across the internet, how do I make sure that nobody's going to be able to listen into the secure tunnel that I build? And then number 3 is using this association that we built between steps 1 and 2 to actually build what's called a security association. The security association is the type of traffic end-to-end that's going to be encrypted, and the methods and such of doing that. So, and then for profit, for South Park and all. All right, I guess I can use the other half of the screen. All right, so first we'll start with step 1, peer authentication. Ideally, we could use an IP address. Theoretically, an IP address would be unique enough. That's the uniqueness around the internet is based on IPs. However, it's possible that an IP address could be spoofed. We see it happen with routing changes, where every once in a while you'll hear about somehow all of Facebook's traffic got routed to Pakistan. Okay, I can't trust that IPs are going to be unique in that sense. That if somebody could just make a routing adjustment and all of a sudden they're a better path to that IP address than you're the real path. So I have to have something on top of that. The 2 biggest ways of doing that is a pre-shared key. And 2 is an RSA certificate. Pre-shared key is elementary. You literally just have the password, and it's shared between two peers before you do anything, hence pre-shared key. Nothing complex about that. You got to make sure your pre-shared key is long enough so that when you stick it into the SHA-1 or MD5 hash, that it builds a deep enough hash to be not easily guessable. RSA certificate is considered way more secure in terms of authentication because you have to use between peer A and peer B. I'm making sure the camera's over there. certificate for this guy and the cert for this guy. B has to be able to say, I trust cert from A. And cert from A, well, A has to be able to trust the cert from B. So typically, you go and you just procure a host level certificate from GoDaddy or, whatever one of the other auths people, or you go in and you dump in your private CA cert into the hosts. Equally secure, provided that you can control your own CA. You have to be able to control your private keys for the certs, etc. That's something that you have to download into the boxes. The risk with RSA certificates is just making sure that when you put a private key somewhere, it's either locked down or it's in a way that it can't come out easily. So in some cases where you would mail a piece of equipment to a site, and that site is secured by certificate-based authentication, they have flash drives that have the cert on them, and so you can mail that flash with the cert and have the iOS unlock the cert if it was a Cisco environment. So those are really the only two ways of doing it. I mean, there's probably a third way, but that's the way we do that. From a technical basis, what we're using is called IPSec I don't have my computer with me, so I don't have my notes that I put together last night, but I believe it's Internet Security Association Key Management Protocol. There's two different versions of the language that this takes place. ISA-KMP is the newer one. The older one was some other method that I don't remember, but it was probably inferior if we're using ISA-KMP. This is the first association that happens between two devices. And the job of ISA-KMP is to both determine authentication and then secondly, set us up so that we can exchange keys. The way that key management or key exchange works is pretty cool. There are a couple of really smart dudes, Diffie and Hellman, and they came up with a strategy for sharing keys that has been proven to be practically unbreakable. You take it's a mathematical function of using modulus and primes and a random number. And you take this guy, you stick it into an algorithm, and this random number is pushed into the algorithm. And what out comes out is just a blurb. Peer A does this. Peer B does the same thing. They come out with Y, 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 and then they share that with each other. So it looks like garbage going across. Now, what happens with the two of these is that A sends his to B, B transforms it sends it back as Y, and then A transforms it again and ends up with Z. And B ends up with Z. And what's interesting about that is what Diffie-Hellman process does is allows two hosts with no prior knowledge of each other to come up with the same shared value based on the randomness of that random number and the uniqueness of a prime. They have to use a prime number that's, 1, 3, 5, 7, 11, 13, 17, going up. But we're talking about primes on the order of 6, 7 digits long. And what it does is it makes sure that the uniqueness of this algorithm is completely dependent on the input of the random number. And then the random number that peer B uses and the random number that peer A uses together become the private key. The Z. Z is then used to build the key set. So this key set then goes over into building process 3, security associations. Ideally, you don't use the same key for very long, because the longer you use the key, the more likely somebody is going to be able to recognize the pattern being the key. You get this huge data set where each little block of the data set was individually encrypted with the same key. Eventually, machine learning will be able to extrapolate the key, and then not only can you use that key to go and unlock the data that was already sent, now you're able to use the key to decrypt in real time. So the idea is that we define lifetimes. So I'm going to go ahead and erase here. As part of this process, we have a lifetime for the IKE, which is the Internet Key Exchange. That was the root part. One of the methods of doing IKE is ISA-KMP. The other method, I don't remember, it's older, it's not used nearly as frequently. So IKE, typically it's like 28,800 seconds?
Yep. It's a default.
Typical 28,800, and then on ESP, which is the Security Association, it's like 3,600.
Mm-hmm.
And then also sometimes they do a bytes limitation as well. So at IKE, we are going to go and restart steps 1 and 2. Every 2,800 seconds by default. The idea of that is that eventually, even Diffie-Hellman is susceptible to key reuse. So we need to restart that process over and over again. So we'll start back up here. Well, the beauty of IPSec is because these timers are large enough and different enough, you can handle re-keying the key ring, putting more keys on the key ring, without messing with the security association. So, we just keep, essentially it is, it's just like a key ring. You got a key with 1,000 rings on it. The amount of rings is determined by the amount of seconds. Divide 3,600 into 2,800, 2,880. That tells you how many keys you're going to use, cycle through before you end up resetting the key ring. And then you just keep adding more keys onto the key ring, cycling through and that. The reason why ESP contains the bytes keyword is because as networks improve in performance, we can start sending more and more traffic in the same unit of time. Eventually, this bytes value could stay the same, but we need to take this number and go down, or take bytes and use bytes as our method of how often we change keys. Most people continue to use time. That's great until you come up with an AI chip or something that's specifically targeted to attack ESP and that. But the encryption strength the key protection is really based on how much data you use before you throw the key away. Okay, then the next part is building a security association. All of this up till now has been a talk about peer-to-peer communication, and it's data agnostic. It doesn't really matter what you use the key for. Security association is what you're actually going to encrypt. It's possible that you would use IKE to form a key and send HTTPS data through it. In fact, they actually do. It's a different process. It's not IKE and ISA-KMP, but it's still Diffie-Hellman, and they use the forget what it's called, the Rainbow or something that was the NSA hack or something, Rainbow Modulus or something. There's some other technologies that use essentially this portion, but don't do IPSec essays on the end. IPSec essays are specifically built for IP. There's a different version of it that's built for IP version 6. But essentially, a security association is your dotted decimal and a port number or a protocol number. So call and a port over to the same thing. Dotted decimal, protocol,
Port.
So I built an SA based on this match. So I could get all the way down to, 192.168.1.1, protocol 47, port 0. That would be a GRE tunnel. It's actually one of the more commonly used things that you stick in IPsec. I could say 192.168.1.1, protocol TCP, port 80. And I could run an IPsec tunnel to secure port 80 traffic. You'll find that Microsoft Windows actually has a built-in IPsec for peer-to-peer communication you could turn on through group policy. They never updated it with new security methods, so it's stuck at like 3DES and MD5 encryption, which is essentially readable now. But it supported setting up these live across the wire. So when you go talk to a Windows server, the first thing you would do would be to build an IPsec tunnel to that Windows server, and so all of your traffic, client to server is encrypted. And one of Microsoft's thought cases on that was, what if we could have our Windows domain controllers sitting out on the internet with public IP addresses and Windows computers at people's homes, and they would just IPsec tunnel straight to the Windows server. Didn't work out so well because it's sometimes NAT tunnels and can break IPsec, and you end up with some issues there. But for the most part, this is what we do. When we deal with a vendor, typically we're setting up IP to IP. I'm sorry, actually, one part that I missed here is the mask. Like a subnet mask. If you specify an individual IP, it's going to be a /32. If you're using a whole subnet range, /24 or /16, etc. So, going into the next part, which would be if we were connecting two organizations, org A and org B, and we have the internet between them, then what we might see is a firewall and let's just go to a router with firewall service underneath it. pretty much device agnostic because IPSec is an RFC. Everybody's required to implement it in basically the same way. Yeah, you can throw in your own parameters here and there, but good luck getting anybody else to use them, unless you're Cisco. Our tunnel that we build here, we can do a couple of things. We can build a typical SA that's just, org A is 192.168.1.x. Maybe org B likes to use 10.0.1.x. So we could plug those into the security association and build that. But there's some limitations in IPSec. One, it doesn't support multicast traffic. So good luck trying to get a dynamic routing protocol to work over. You with 255.255 or 225.0.0.2. I don't have an SA for that. Or maybe I build an SA for that multicast traffic. It's not the same SA as what you just used to build this. So that's some of the problems that you end up with IPSec is, if you have a tunnel, the tunnel is built for the traffic going over it. If you try to use some other traffic to go over that tunnel, you can't. So you have to create a different tunnel. So how can that tunnel be used to control traffic in this tunnel? It ain't going to work. So
GRE.
GRE is a prime example of what people will use, generic routing encapsulation. The GRE is a Cisco standard that is kind of sort of used generically in the world. There's an IP tunnel. There's an IP6 IP tunnel if you're trying to do IPv6 over IPv4. The newest one is actually called a virtual tunnel interface. VTI, virtual tunnel interface, and that's what all the new equipment's using. It's it's really kind of strange the way it works. The problem I just described with security associations being very locked down on the type of traffic that you go across it. Virtual tunnel interface has pretty much said, well, let's modify that a little bit. They've gone in and played with the underlying stuff, and I'm not going to get into it because, frankly, I haven't really read up enough on it that I completely understand it. But a VTI is a way around some of this exclusiveness. So, going back into, that's kind of how we use SAs, get into some of the meat of an SA. Okay, so a security association is actually unidirectional. Which means that for bidirectional communication, you have two. And those are called, the SA is labeled with what's called a SPI. And again, someone would have to go look that up because I can't remember what that means. Because my wife is bringing me my laptop as I speak. So Wilson, would you go look that up?
Doing it now. Yeah.
I believe
Has.
let me take good notes.
System packet interface. Oh. It's security parameter index.
Okay.
Add it to the header while using IPSec for tunnel.
Okay. So I've got an SPI for that direction, and I've got an SPI for.
Yeah.
Okay. So I'm actually, my session, my one security association that I think about is just going to be these two SPIs. And SPI is referenced as a hex number. And this SPI would be a different one. Now, also, the keys are different. Because the guy that creates the SPI creates the key, and then they use the Diffie-Hellman process to send that key over to the other side through IKE, which we covered, ISA-KMP relationship. So, we attach a key, and that is shared this way through IKE. That's key 1. Sent this way with IKE. IKE was actually an improvement along the old way of doing it, where I would specify the key statically. It really sounds like a difficult thing to do when you start talking about hundreds of tunnels, and I want to think about lifetime and all that type of stuff, because I got 2 keys, different keys on each side. So I have to go in and specify this SPI and map it to a key, kind of like the old web keys from wireless. We'd have 4 hexadecimal keys. You basically would have to do that here. IKE allows us to do it, automatically. I think how are we on time? Half hour? Actually, I went through this a lot faster than I thought. Does anybody have any questions about anything we've covered so far? Okay. All right. I guess we could look at the packet headers and then talk about things like MTU and some of the fun stuff that happens with that.
Eric, it's Bert.
Hey, Bert.
Hey, the unidirectional, is that exclusively for security purposes?
It's the way that it's set up. Theoretically, the unidirectional would allow you to have 3 hosts and build traffic to go around the ring. I don't know of a use case where you would want that, but it's possible. You could actually set traffic to bounce around. But the unidirectionalness of IPSec is one of those things you have to watch out for, because occasionally you will see, like especially when you cross between different vendors of equipment, like a checkpoint to a sonic wall, or a sonic wall to a Palo, or a Palo to a Cisco or something, that they will treat building VPNs slightly different. Case in point, if org B wants to encrypt, they want to build, or let's start over here too, org A. If org A is 192.168.1.x/24, and org B is 10.1.0x.24. Let's say I don't want to build a session that allows org B and org A to see everything on everybody's side. They only need to share access to a web server in org B. That org B has 10.1.0.4.5 and .6. .3 is super private, so we definitely don't want access to that. And .7 is also super private. So we got to make sure that we do not even think about giving somebody the ability to see .7 or .3. So we got to constrain across here. If I was on a sonic wall, per se, I have an experience on sonic wall, so I can say this, 10.1.0.4 through 6 is a valid way of building a security association. If you can find the subnet map that allows you to define that in the CIDR range, I'd like to see it, because it's going to include 3 and 7 if you try to do a /29, which is the smallest range that would encompass those 3 hosts. Or, yeah, I'm sorry, /30 would, but it would also include 7. So I can't do a /30 because that would include one of my super private hosts. So I'm going to have to assign this as 3 individual essays as /32s. Over here, maybe the range of hosts that they want is .0 through .31. That can be summarized. That's a /27. So my essays should be /27, 192.168.1.0 to .4/32, .5/32, .6/32. So this guy here would be programmed with 3 SPIs, and this guy would be configured with 3 SPIs. The unidirectional thing comes into play is, what if you did something like, maybe instead of doing 4, 5, and 6, maybe we were 4 through 8. I could do the 4 through 8, 4 through 7. I could do .4 through .7 as a /30. And so over here, instead of 4, 5, and 6 /32, I could actually make it to a /30. But I don't have to. This guy here could just add another .7/32. This guy could have the /30 to the /27 going the other way. Because the SPIs are unidirectional, both ways will enable traffic to flow, because they're in different directions. It'll still match. In the routing table on the work B's router, it's going to see the /27 as a route. And over on org A, it's going to see 4 /32s as a route. They both are the same exact addresses. But over here, you have one SPI, a /30 to a /27. And over here, org A going over here, you have 4 SPIs, /27 to a 32, 27 to a 32, 27 to a 32, and 27 to a 32. Just gives you options. It's not a strict requirement. So it being unidirectional actually is probably more important for who gets to set the key. Whoever, when I create the SPI in this direction, this guy is the key maker. And then he transfers the key over here to say how to unencrypt it. Does that answer your question, Bert, or did I ramble too much?
Yes, thanks.
Okay. All right.
There'll be more.
And that's the thing that Wiley was running into yesterday, is one organization wanted to, they gave us some weird range that's not summarizable in any way. And really, did it work when he made all
It
those
was
last
131 through 156 or something like that.
There was no way to do that, so we just had to do the entries.
Did it work when you did that?
Yeah, he's having some issues on his end, but hopefully we get it resolved today.
Okay.
The Palo Alto and Cisco handshake isn't always as nice.
Yeah, that's common. That is the one thing about IPSec tunnels, is because there's a lot of key exchange and setup in there. If the tunnel's down and you try to send traffic over it, you're going to have drop. You're going to have sometimes as much as 2 or 3 seconds of drop. It's actually common for IPSec tunnels to get stuck in a dead end, where the ISA key management is in an end state and won't create more tunnels or won't create more keys. And so the Security Association runs out of lifetime and then
Done.
It's got the key exchange up and running, but it's not spitting out any new keys. And so the system doesn't kill it and start over. So we've had times where an administrator has to log in to the firewall and kill the session, clear the key management, and then it'll create a new session and go over. So sometimes you want to actually drive your session time for ISA KMP down to the floor, maybe every hour or every 2 hours, if it's something that you don't want to babysit. It just depends. The more tunnels you have in the organization, the more you're going to be managing dead sessions.
Right. I think it's important to note too,
out loud is that org A and org B for phase 1 and phase 2, which he was explaining earlier, have to match on the config.
Yes.
There's no tolerance there. Your only tolerance is in your routing.
That's a good point, Wiley. I forgot to even talk about protocols and encryption methods. Okay. All right. We can go back and talk about, go all the way back to key management. IKE and ISA, KMP. Okay, so we talked about how we're going to figure out who's who. Now we have to talk about how we encrypt stuff when we information share. When we take our key and we send it across the wire, and for the sake of this, let's talk about pre-shared key, because that's easy, it's just the word password. When we take our key, which in this case is password, yeah, it's the same luggage combination that I have, and we pass it across the wire, we're going to pass it through something like MD5, SHA-1, SHA-256, etc.
Group, whatever.
ASA KMP is agnostic. If both sides know how to, there's like a bit number in here that references the encryption. But it's set up in such a way that if I use a vendor-specific encryption, I just use a vendor-specific code to reference that. And then if both sides agree to use the same code, they'll reference it. The beauty of these, they're called hashing. They're non-reversible. Usually it takes it's usually multiple cycles. I take my word password and then I flip a bit and then I pass it back to the beginning, and that causes, the second pass is to translate two letters and, do a couple of things, and eventually I've ended up with a hash that's non-reversible back to the word password. Unless you're MD5 and that's subject to the birthday attack. So then the other guy takes his key, and let's say that he misunderstood and thought we were doing some leet speak or something to put PASSWORD, and he puts it in here. The difference in the hash is going to be phenomenal of one character. Instead of the hash being A, B, C, D, it's now going to be like 3A01. It's going to be ridiculously different. That's the purpose of hashes, is that there's no way for us to see that this got hashed to that and this got hashed to that. So when I look at the hash, I can go back and figure out what I originally put. So we have to make this correction, and we got to change that to O, and then our hash comes out to being A, B, C, D. Each guy looks at the hash from the other guy and says, hash matches my hash, therefore he has the same password, therefore, yep, we are authentic. Now we can start doing our Diffie-Hellman to set stuff up. Now, Diffie-Hellman has different groups, what it's called. Diffie-Hellman. We have, and the groups correspond to the, say it's group, does it go up to group 14 or group 12? I guess group 5 to 14. Or
I've seen 20 and 21 used
yeah,
now, but group 2 is the most popular. We're trying to push everybody to 5.
Group 5 is the minimum standard now.
Yeah, it's definitely the minimum.
What the group defines is the size of the prime number. Remember that
Prime number.
that calculation I showed you, which is random number times the modulus of this crazy big prime number. And what modulus is if I divide that number by 2, I get the remainder. Or if I divide this number by this number, the remainder is what modulus means. So if I said mod base 2 of 3 would be equal to 1, because there'd be 1 remainder left over if I divided 3 by 2. 2 divided by 2 is even, and there's 1 left over, so modulus 1. So when I take a modulus of a prime number, I'm going to get some number out of it that's equally as ridiculous in size. So the group here directly relates to CPU processing required. Higher the group, higher your CPU, higher your load on your firewall. Understand the consequences of that. We are making firewalls that are capable of building hundreds of thousands of SAs. If you build hundreds of thousands of SAs and you use, group 320 or 3022 and it's some stupid number, it'll take more time to calculate the new key than the IPSec tunnel would live for. However, it's a race against the competitor. If I need to protect my stuff and I know the competitor is invested in machine learning and they are capable of cracking complex keys, then I might want to spend more on upgrading my key tunnels to using a higher modulus number. The Diffie-Hellman is the low-hanging fruit. The NSA had a leak a couple years ago, and one of the things that was published was that there's some, I think it's called the rainbow or something. There's a number chart that the NSA published as part of the FIPS documentation that says you want to use numbers in this area to achieve the maximum encryption. And then it came out as part of the leak that using numbers within that area actually only looks secure, but the NSA has a way to, to birthday attack that area of sorts that they can attack that number and actually get the Diffie-Hellman, random number back.
Mm-hmm.
Are you talking about using rainbow tables?
Rainbow tables, that's the name of it, isn't it? Oh, no, not rainbow tables. No. Okay, look, someone's got to look it up. It's like Diffie-Hellman group 22 and 24, I think, are the ones that are using it. And it's had limited adoption since the NSA was hacked. Or not hacked, but leaked. I think it's like...
Diffie-Hellman crack.
Elliptic curve, that's the name. The elliptic curves. There's a unique issue about it. If you want to read up on it, it's a very interesting SPY versus SPY type of deal. But a lot of businesses tend to use Group 5 or Group 7. I think is the next one up because it's that makes the jump almost to like 24. I think it's 2048-bit is Group 5, and that's considered significantly strong enough for the 3600 seconds mark in IPSec.
Yeah, Group 5 has 1536 bit case.
Group 5?
Yeah.
Okay.
Yeah.
The next group up is, I think, what I've used, the 2048 on most of the stuff that I like to do. But yeah, definitely shy away from Group 1 and Group 2 unless you want to use very short lifetimes, which then again, you end up spending more CPU time recalculating keys because you're not making your keys for as long. Okay, so then IPSec. Now with the SHA, the hash, and the Diffie-Hellman group, we've now transferred our keys. We're making the unique keys appropriately. So now we can go down into, we leave IKE and we go down to IPSec for encryption. Not very good with a whiteboard today. IPSec, SA, encryption. Okay, so here we have a couple of things. One, we usually call it a transform set. Within the transform set, we have the encryption suite. And we have the the digest authenticator. I forgot the exact name for it. It's a hash. And then we also have whether or not we're doing encapsulation
Authentication.
or authenticated headers. ESP or authenticated headers is a very simple choice. You're always going to encrypt the payload. Do you encrypt the header? Question. If you don't encrypt the header, then you essentially are sending the source IP and the destination IP and the IP protocol number in clear text across the internet. Okay, so the whole world sees your public range or your private IP range. Decide whether that's important to you or not. Most people, like probably 99% of the tunnels I've ever built, maybe even 100%, use encapsulation.
Right.
It's just easy. It's all random garbage when it goes out on the internet at that point. The two big ones are actually encryption suite and the digest. The encryption suite is any number of things. You can actually send it in clear text, which is useful if you are having issues and you need to diagnose.
So I took.
Clear text, you can do, what's the 3DES? You can do DES, 3DES. 3DES has a funny story about it. Regular DES was 56 bits, and the government was kind of like, that's child's play. And then the industry came out with 3DES, and they tried to give it to the government for security. You guys really have to take a look at this. And the government said, nothing developed by the private sector is good enough for government work. Then the banks picked up on 3DES, and then somebody with the NSA was like, holy crap, we can't even break it. Then they tried to go after it and said, no, nobody can use it. We're controlling it for export, all this stuff. But by that time, it was international, all that. Well, now 3DES is so old that nobody wants to use it because it's old. It's hackable, based on computer power. The new standard, which came out of an NSA consortium project because they learned their lesson, is essentially I think they call it block ciphers. And that would be AES, Advanced Encryption Standard, Blowfish.
That's my password. Stop.
Both of these have incredible CPU performance over DES and 3DES because they're block-based and not like waterfall-based. Like triple DES, you can really understand it's you do whatever you do in DES, and then you pass it back to itself 2 more times. It really makes it pretty secure by comparison to the original, but it's way more intensive in architecture. So it required specialized hardware. At one point, when you bought a Cisco router, you'd buy the encryption module to put inside of it so that it would like triple your encryption performance on the chassis. AES can be done in an x86 processor almost as fast as a specialized ASIC. So incredible gains when it comes to processing SSL on the workstation level. AES. Yeah.
What is the bit encryption for AES?
It's variable.
Is it?
Glad you asked.
128, 192, or 256?
Is 256 the highest?
No.
No.
The standard doesn't define a maximum. However, there are all of the, the encryption geeks that are out there will say that it's a diminishing return, and then also you run the risk of exposing too much data encrypted by the same key. Block ciphers use this method. I'm going to have bits, or I'm going to have hex. But I take my data and I structure it out into these blocks. And then say my data was only long enough and I left with 2 blocks at the end, then you pad it. There's a formulation for how you pad data, because the block cipher requires a full block to work. And then we're literally talking about up, down, left, right, A, start type of block shifting. Maybe the block standard, your encryption key. The encryption key is just how you shift the blocks or how you replace the blocks. So if my encryption key, could be as simple as if it's a 1, I shift left. If it's a 2, I shift right. If it's a 3, I shift up. 4 is shift down.
It's the little orphan Andy decoder ring.
Yeah, 5 is replace with a 0. 6 replace with a 1. 7 is an XOR, which would be just flip the bit. That right there could be my key. And all I got to do is just change the numbers that associate with these, and then I just run it through the block. Computers can do find and replace on a memory in real time. As the data is just passing through the module, bits are getting flipped and it spits it out. So block ciphers are incredibly fast, incredibly secure, because the key is, or the method of operation is simple. Kind of the Occam's razor approach. Over here, if you look at an encryption block diagram for 3DES, it's got triangles and octagons and stuff to do different processes with different pieces of the data. AES and Blowfish, the only difference between the two is like whether the block was formulated from the left to the right or if it was formulated up to down. They're almost indistinguishable, but somebody probably paid a politician more. AES is typically found in 128 and 256. There are some variants of 512. The 256 and 512 have been labeled as an approach with caution. AES 256 is considered max security, but there's one of those things where they think that there may be a collision possibility as you go up in key strength, but our computers are not yet strong enough to tell if that's possible.
Yeah, they're only talking about 256 most of the time.
So,
and 488 on Blowfish.
So go with the 128 or 256 is typically the suggestion. AES has made its way into SSL, and TLS 1.1 or something is when they opened up the universal encryption possibility. And so this is the new standard. And then we end up with at the same time, once we do the whole block, we slap a hash on it, and we stick the hash again is either MD5, SHA-1. 256, 512, etc. You can go up as high as the platform supports. And so the idea here is that once I have my encrypted package, then I'm going to hash that package and stick the hash in front of it to make sure that it doesn't get garbled in transit. It's kind of, it equates to a checksum, as well as making sure that nobody was able to tamper with the data. The digest includes the headers and when you encapsulate it, so that if I de-encapsulate it, if somebody was able to create a collision, the risk of changing some data is very great. But the more stuff you include in the digest protects the packet from being attacked and making it to its final destination in a way that the data would be to be believable. Again, authenticated headers is not used very often because in authenticated headers, all we do is we just encrypt the payload. We don't encrypt the 192.168 to 10.0.1. Yeah, I guess we're about out of time. I would show some actual packet captures, but I left my computer at home, so that's not going to happen. So I can kind of draw out what it looks like on the wire. And then maybe I'll email out a PCAP file. Okay, so on the wire, you're going to have your layer 1 header all the time. Layer 1. If I could actually write 1 instead of an I. That could be Ethernet, it could be PVP, it could be, or PVP is layer 2, it could be some sort of framing. We're just going to skip all the way to layer 3 because that's what matters. So in layer 3, you're going to have the peer. Peer A to peer B. And that's IP. And that the protocol, once you're encrypted with ESP, is going to be protocol number 50, which is a very specific thing that a lot of people on the internet like to mess with now because it stands out like a sore thumb. Traditionally, your firewall didn't support this very well. And some firewalls still don't. A lot of your DSL modems and crap at home, they, for some reason, refuse to build NATs around ESP50. So there are a number of ways that vendors have gotten around that. SSL VPN is the laziest way of doing it. You could encapsulate ESP into UDP because ESP is non-required delivery. So if you're stuck in a TCP packet, which is what HTTPS tunnels are, you have to guarantee that every packet hits the other end, which your network card now does through, we've had TONICs now forever. The problem with it, the reason why we have such crappy performance with HTTPS is that the effective throughput goes down as the latency goes up. We've actually tested that. We put our client on the actual edge firewall here, like on the internet edge, and we were able to get like 120 megabits through the VPN client. You attached to the cable modem right next to it, which added like 20 milliseconds of latency, and we went down to like 7 or 8. That's just what happens when you add latency into something that requires delivery. ESP50 does not expect to be seen at the other end. It doesn't even require to be seen at the end. You could drop 5 packets and you could still unencrypt the 6th. Inside this packet, protocol 50, you have an ESP header. The ESP header is the SPI. Underneath that, encrypted data. Do I have enough to decrypt this? Yes, because they gave me the SPI. So then this guy comes over here, when he receives that packet in, he just looks at the SPI header and goes and looks at his key ring and says, yep, I can unlock that, unlocks it, and decodes the encrypted data and routes it as appropriate. So that's an ESP packet. The only difference between this and an AH header is that AH has an extra layer here. You still have the SPI because you still got to know what security association to use to unencrypt it. But in here I have my inner header. Anyone tell me why that might be useful? What if I want to filter the packet before I decrypt it? I mean, that's really the only time I've ever thought of as being useful. If we were to, well, I guess we could leave that as ESP. If it was ISA KMP, layer 1's the same, layer 2's the same, layer 3 is the same. Layer 4, actually layer 3 is not the same. Layer 3 would be UDP 4500 if you're NAT, or actually it'll just be 500 if you're not. 45 or 500 if you're NAT, if you do not need NAT traversal, and UDP 4500 if you need NAT traversal. The signal there is that inside the data of NAT traversal, you're going to put real IPs of the devices. If this packet passes through a source NAT, like I'm tunneling from my desk here at Health First out to the internet somewhere, you're going to pass through our Palo Alto firewall on the edge, and your public IP is going to change. If you just send a UDP 500 packet, the receiving router is going to look at your source IP and try to match you to a peer table. If you use NAT, there's an extra field in the UDP payload that would put the real, the peer's authentication information in there. If you're authenticating based off of an RSA certificate, it's not necessary to use NAT traversal for that particular function, but there's also something called IPSec version 2 that has a bunch of extra extensions and all that. So NAT UDP 4500 it was like kind of like the kludge to fix the underlying issue. IPSec version 2 puts actual fields in the payload so that you don't have to rely on the header. So you're not needing it as much anymore, but a lot of vendors are still using the 4500 because it's just the de facto standard for when you're tunneling out from behind a firewall. Layer 4 is, let's see here, UDP, and 500 is actually down here. And this is where, layer 4 is where it's labeled as an ISA KMP packet. In the payload, we're gonna send multiple packets for the MD5 or the hashing, and then we're also going to do our Diffie-Hellman. We're at DF instead of DH, and then we're also going to send our keys in that 500. And so as time goes on, ISA KMP is a separate process from ESP. So we're going to continue to just change our keys. And then when that SPI expires, one of the important things is that when the SPI expires because of time, it's expected that the new SPI has already been stood up so that you can have hitless transition. And that's also part of the reason why we have unidirectional tunnels. Because ISA KMP will stand up multiple SPIs with the same source and destination. So that if a packet comes in on an SPI, it's ready to go. So when this SPI comes up, it's maybe idle for 10 seconds before this one is torn down. But as soon as it comes up and the far side has agreed to begin to use it, I'm going to send my traffic over that, and I'm not going to use this tunnel anymore. I'll start tearing it down. So it enables both sides to end up using their own timers for when they expire tunnels. I think that definitely concludes the time we have. Are there any final questions? Who else on the phone?
Joe Burris, and a lot of Chris Burks, and Paul was there for a little while. Cool.
Is this useful?
Yes, very.
Definitely.
Yeah. I don't mind doing it just for fun if anybody wants other topics to cover. But if there's something specifically that we do that you want to learn more about the packet analysis for, nuclear reactors. Next, I could talk about nuclear reactors too.
I would rather you didn't.
Eric, maybe you should include something to do with the cloud too. I don't know if that's possible.
I'm sorry, say that again, Sunil?
Eric, yeah, I was thinking maybe we should do something for the cloud too, like, get some background on what type of protocol, direct connect, peering, things like that. It might be
Okay,
helpful
all
for the
right.
team. We're exposed, on the back end in terms of security for the cloud, things like that.
Okay. I guess the next one that's primed is that maybe next week, I'll get with Sean to make sure our drawings are up to date for the direct connect and VPN. And then we can look at how our new direct connect with VPN for dual data center backup is there. And we can hit on how BGP works with path selection and that. That's a good one.
Need to go over the load balancer sandwich as well.
I'll let Sean kind of talk into that one. I know Sean and Jim have been trying to do lunch and learns. They keep getting canceled because of overlapping stuff.
Yeah.
But maybe we could do that one, that more. Cool. Yeah. Cool. Thank you, guys. Thank you.
Very good.
Thank you, Eric.
Thank you.
Yep.
Thank you.
Let's see, where's my Zoom meeting in progress? And
Everybody got the little orphan Annie Dakota